everyone! Now that we've seen electromagnetic radiation and how some types are ionizing, some are non-ionizing, we're going to take a look at nuclear radiation, where all types are ionizing and therefore dangerous. The first one I want to look at is alpha particles, and we can see a picture of alpha decay over here on the right, where a nucleus gives off an alpha particle, which is 2 protons and 2 neutrons, and it's the same as a helium nucleus. So an alpha particle is actually quite large. In fact, it's the largest nuclear radiation particle of all the nuclear radiation particles. And because it's so large, this is a kind of decay that will happen when you have a very large or massive nucleus that's unstable because it's too large. It will give off that large alpha particle in an effort to become more stable, to drop mass quickly and become more stable. Now, it's also the least penetrating of all the nuclear radiation particles, and that's because, again, it's so massive, it's so big, that it can be stopped by air or skin or paper, right? It just can't travel as fast when it's so large. It's also, even though it's the least penetrating, it is the most ionizing, which really means it should be the most dangerous. But because it cannot penetrate, it is not as dangerous as other types of radiation particles. So it is the most ionizing. Now, consider then what it means for the radium girls who were actually ingesting the radium-226, which was an isotope that undergoes alpha decay. Imagine what it means for them to actually be ingesting that. Yes, it's not very penetrating, but it is the most ionizing, and at that point, it's actually in their system, in their blood system, in their internal system, to wreak havoc on their bodies. I'm going to take a look at what it looks like to balance or write a balanced nuclear equation for alpha decay. Now remember that in balanced nuclear equations, the idea is to show that the protons and neutrons are conserved, right? So that total, the protons and neutrons are not created or destroyed in a nuclear reaction. Totally, they're conserved. That means that our mass numbers on the left side of the arrow must equal the mass numbers on the right. The atomic numbers on the left side of the yield sign have to equal the atomic numbers in total on the right, okay? So we're going to take a look at radium-226, which again is the radioisotope used in radium dials by the radium girls. Now we see radium-226, this is the mass number, so we know that 226 is our mass number. Radium on the periodic table has an atomic number of 88, so 88 is our atomic number, and we can see the chemical symbol of radium over here is Ra. All right, now we're going to look at what the decay particle is that's formed. Well, that's easy enough because we know an alpha particle up here is 42He. So mass number 4, atomic number 2, and chemical symbol He. Now we just need to figure out what the formula or what the isotope notation for the daughter nucleus is, right? The new nucleus that's formed from the decay of radium. So the idea is our mass numbers on the left have to equal the mass numbers on the right. If I have 226 for my mass number on the left, and so far I have 4 for my mass number on the right, I can subtract. 226 minus 4 gives me a mass number of 222. I can do the same thing with my atomic number, right? 88 on the left, I have 2 so far on the right, so 88 minus 2 gives me an atomic number of 86. An atomic number 86 on the periodic table is radon. All right, now the next type of decay I want to look at is beta particles. And we can see beta decay over here, right? So the picture over here where a neutron is turning into a proton and an electron, okay? So beta particles are very small. Unlike alpha particles, which are very massive, beta particles are very, very tiny. They're fast moving, and they're really a high-speed electron, and that's why they're so small. Beta decay, unlike alpha, which is decaying when the nucleus is too large, is really decaying when a nucleus has too many neutrons, which is why we see in the picture here, a neutron is going to turn into a proton and an electron because there's too many neutrons, and therefore the isotope is unstable. Beta particles are more penetrating than alpha because remember they are smaller and faster. These can actually still be stopped by aluminum foil, thin wood, or plastic, right? So they are stopped by some substances, but not as thin of substances as are stopped by alpha particles. they are less ionizing than alpha particles. So yes, they can penetrate more, but they actually are less ionizing, which kind of balances out. So let's take a look at writing a balanced nuclear equation for sodium-24. We call this beta minus decay because an electron has a negative or a minus charge. So sodium-24, I can see here, has a mass number of 24. If I look on the periodic table, I'll see that its atomic number is 11. And I see that the chemical symbol there is Na. Again, I'm going to fill in the decay particle first because that's the easy part, right? We know this is a high-speed electron, and a beta particle, if it's an electron, has no mass, right? So mass number of 0. Its atomic number, because it's an electron, is actually -1. And to represent it being an electron, the chemical symbol we give it is lowercase e, right? So there's our beta particle, or our electron, that's being emitted during beta decay. Now again, I'm going to try and figure out what is the new mass number of my daughter particle. So if I have 24 on the left, 0 on the right, my mass number has not changed. If I have an atomic number of 11 on the left and -1 on the right, this is a little different. This time when I subtract 11 minus -1, that's really 11 plus 1. So that gives me an atomic number of 12. And atomic number 12 on the periodic table is magnesium, right? The third type of radiation we're going to take a look at is gamma radiation. Now, gamma radiation is extremely high energy radiation, extremely high energy. And this actually behaves more like a wave, like we see with the electromagnetic radiations, right? Because gamma rays are electromagnetic radiation. Gamma radiation is released whenever you have alpha or beta radiation, or most of the time when you have alpha or beta radiation, gamma radiation is given off as a byproduct, as leftover energy. It's the most penetrating because it's highly energetic photons from the electromagnetic spectrum. And because it's the most penetrating, it actually takes concrete, steel, or lead to stop this gamma particle. It can go right through the paper, right through the plastic, and be stopped by concrete, steel, or lead. And it is the least ionizing. So again, we're balancing out here, but because it's the most penetrating, it really ends up being the most dangerous because it's most penetrating, right? Yes, it's least ionizing between alpha, beta, and gamma, but it has the strongest penetrating power. All right. Now, the last type of nuclear radiation I want to look at is positron emission. Positron emission is actually happening, if we look at the picture here, when a proton inside the nucleus is converted to a neutron, it releases a positron and gamma radiation, right? So the proton here is turning into a neutron and giving off a positron and gamma rays. Positron emission this time occurs when a nucleus has too many protons, right? So beta happened when it had too many neutrons. Positron happens when the nucleus has too many protons, which is why here the proton turns into a neutron. And it's unstable, so it's going to undergo positron emission or give off a positron. Now let's take a look at an equation here, and this is for manganese 50, not magnesium, but manganese 50. I see that my mass number here is 50. Manganese on the periodic table is atomic number 25, and its chemical symbol that we see there is Mn. Now this time we have a positron. So this is very similar to an electron, except with a positive charge. And that's why up here you see E with a positive charge. So a positron, again, has no mass. So the mass number is 0. And this time, instead of the electron, which is beta minus, positron is called beta plus because this is a +1 charge. A positron is positively charged. And we still have E to show it is the positive form of the electron. Now again, we're trying to balance out our mass numbers on left and right. So if I have 50 on the left, 0 on the right, that gives me 50 as my new mass number. If I have 25 on the left and 1 on the right, then I subtract 25 minus 1, and I get 24. Atomic number 24 on the periodic table is chromium. All right, and there's our balanced equation. Now, isotopes, radioisotopes, isotopes that are unstable, will decay at different rates. And this is what we refer to as their half-life. Half-life is the time required for half of the nuclei of a radioisotope sample to decay, right? Half of the nuclei to decay. Now, we have very different rates. If you look at something like hydrogen-7, it has a half-life of 2.3 times 10 to the negative 23rd seconds, which I've actually written out for you here, right? So very, very fast half-life. It is decaying very fast. Tellurium-128, on the other hand, has a half-life of 10 to the 24th years. Again, I've written that out here, right? This one takes a long time for half of those radioisotopes, or half of the nuclei of the radioisotope to decay. Now let's look at what the radium girls were using. Radium-226. Radium-226 has a half-life of 1,600 years. So if we look over here at the picture here, radium started being used in radium dials in 1917. So if we have all of these radium nuclei, radium-226 nuclei in the year 1917, then 1,600 years later, in the year 3517, we still have a lot of radium-226 left over. Another half-life passes, another 1,600 years. Now you still have, in the year 5117, quite a few, 25% of those radium-226 isotopes left over. For this reason, when one of the radium girls, her family gave permission, you can see this quote down here, her family gave permission for her body to be exhumed and researched by Argonne National Laboratory near Lamont for study, because this was the ability to study what happens when a person ingests radioisotopes. And the family was told that they brought her body back encased in lead because she was still so radioactive. They say that the radium girls are still glowing in their coffins with a soft luminescent glow that we see typical of radium-226 because its half-life is so long that they still have a lot of radium, almost all of the radium inside of their bodies, which is really, really bad. All right, so we've talked about different types of nuclear decay. Now I want to look at fission versus fusion. Now we have seen fusion as a nuclear reaction that happens in the sun, but let's compare this with fission, which we've actually used here on Earth. So fission is defined as the splitting of a large nucleus into two smaller fragments. Okay, so you have a large nucleus and it splits into two smaller fragments. Fusion, on the other hand, you already see is actually the combining of two lighter nuclei to make a larger nucleus. Okay, so splitting versus combining. The fuel sources for fission are most commonly uranium-235 or plutonium-239. All right, so they do exist here on Earth, right? So we can use them. Fusion, on the other hand, even better, has a fuel source of hydrogen. Well, we have tons of hydrogen on Earth, right? We have tons of water, so we have tons of hydrogen. So that bodes well for the future of fusion being used as an energy source. Right now, fission is our energy source, and it's used in nuclear power plants. We also see it being used in the atomic bombs. So the bombs that were dropped on Hiroshima and Nagasaki in Japan, those were atomic bombs. They utilized the energy of fission, of splitting a larger nucleus into two smaller nuclei. Fusion, on the other hand, we've seen really only happens in stars. Not that it only happens in stars, but that's where it happens continually. We have harnessed fusion energy for hydrogen bombs that have been tested worldwide in different countries' nuclear programs, including the United States. But we have not figured out yet how to harness fusion as an energy source on Earth. Okay, so here's a reaction of fission. We have a neutron bombarding a large nucleus, and this is a uranium nucleus. So it hits the uranium nucleus, causing that uranium nucleus to split into two lighter nuclei and giving off a lot of energy and actually 3 more neutrons, okay? Which then can bombard more uranium nuclei to split them and produce more energy and 3 neutrons. So it can keep on going in a chain reaction. In fusion, we have 2 hydrogen isotopes, deuterium and tritium, and they combine or they fuse to form 1 nuclei of helium and a lot of energy and also a neutron, right? So combining 2 lighter nuclei to form a heavier nucleus. Now the pros and cons that we see for fission, the pros are that It's about 1,000 times the energy of burning coal. So it's a lot more energy than burning coal, and it doesn't give off any greenhouse gas emissions. Fusion is even more times the energy of burning coal, millions of times the energy of burning coal. Also no greenhouse gas emissions, which is huge, and it uses hydrogen as a fuel source. And again, we have hydrogen everywhere. The cons, though, is that fission produces a lot of nuclear waste, and we have to store that very long term because it takes so long to decay. There's a potential because of that for nuclear accidents, right? For spilling, for what we saw in Fukushima. So nuclear accidents or terrorists making dirty bombs, because really, if you know how to enrich uranium, you can make dirty bombs. And really that puts a lot of power into the average person's hands, which is terrifying, really. Fusion, the cons are that it requires temperatures of millions of degrees Celsius, which we see in the sun. We can't sustain that here on Earth. So we can't yet utilize it for an energy source on Earth, but we're hoping to get to the point that we can. That is it for the pros and cons. Now let's take a look at balancing fission and fusion reactions, just like we did above for the nuclear decay equation. So I'm going to fill in, we already have our mass numbers here, so I'm going to fill in the atomic numbers. Since this is hydrogen, they both have an atomic number of 1. And then again, we need to figure out what the new mass number is. Well, we have 3 plus 1 on the top, so we have a mass number of 4. We have 1 and 1 as our atomic number on the bottom, so we have, that should be 1 plus 1 equals 2, right? So we have 4,2 helium produced. We have 2 lighter nuclei, a mass of 3 and a mass of 1, combining to form a heavier nucleus with a mass of 4. So this is fusion, right? 2 lighter nuclei, 1 larger nucleus formed. The next one, we have uranium-235, and uranium has an atomic number of 92. It's going to be bombarded by this neutron. Well, a neutron is a neutron, so it doesn't have any protons, so its atomic number is 0. What's going to form is krypton 92, and krypton has an atomic number of 36 on the periodic table. And it's also going to form 3 neutrons. Again, a neutron has no protons, so its mass number is 0. That 3 in front of the neutrons tells you that there are 3 neutrons, not just 1. So it's the equivalent of 1 neutron plus 1 neutron plus 1 neutron. And therefore a mass number of 3 over here, okay? So now when I have to figure out the daughter particle, we have 235 plus 1 on the left, 236, and we have 92 plus 3 on the right, 95. So 236 minus 95 gives me 141 as my mass number. For atomic number, I have 92 plus 0 on the left for 92, and I have 36 plus 0 on the right for 36. So 92 minus 36 gives me 56 as my atomic number, which is barium. Now, here I have a heavy nucleus being bombarded by a neutron, and it's splitting into 2 lighter nuclei. So here I have fission. Larger nucleus bombarded by a neutron splits to give me 2 lighter nuclei. And again, more neutrons are produced to bombard more nuclei for more fission, okay? So this reaction can keep on happening as a chain reaction that continues and continues and continues until all the fuel, or the uranium-235, is used up. That's it for fission and fusion and nuclear processes. I hope that was helpful.